Ahoy hoy, Mr. Nickerson here, and we're back again here in Chapter 9 to start with a few flipped lessons. Right now, if you want to take out the paper you received in class, and we'll begin. Alright, we're going to start off today by talking about factoring and greatest common factors. And it's some terminology that you have heard in the past. First few things we got to get through, some basic definitions. And most of these definitions date you back to when you were in elementary school, actually. A prime number. Prime number is a whole number which is greater than 1, and it only has factors of 1 and itself. Okay? 1 and itself only. So examples, 2. 2 times 1 is the only factor of 2. 3, 5, 7, etc. Okay, pretty familiar with prime numbers. When a number is not prime, it's known as composite. A composite number is a whole number greater than 1, and that has more than 2 factors. So it's going to have more than just 1 in itself. Will have additional factors. So if we look here on the first example, letter A, that would be pretty basic. Going back to your elementary days, 36, we know that is a composite number. And the reason, 36, we know we got 1 and 36, 2 and 18, and we can keep going down the line. 3 and 12, 6 and 6, 9 and 4, and you can see we have plenty of factors there. We know it's composite. For letter B, 23, we think about it, 23, 23. All we got is 23 times 1, so we know it's a prime number. And that's pretty basic, going back to what you've learned in elementary school. Alright, the next concept we'll talk about is prime factorization. Prime factorization is when a number is expressed as a product of the factors that are all prime numbers. Only using prime numbers and only using multiplication. Let's talk about something you have learned in the past. The prime factorization of 90. Well, probably there's 2 common methods that people do this. And probably when you were back in elementary school, you started with a factor tree. And some people would say, well, what 2 numbers multiply to 90? The easiest way to do this, you want to choose the lowest prime number that would go into 90. The smallest prime number that goes into 90, 2. 2 and 45. And you keep going down the line. Well, I know that 45, 2 doesn't go in there, but 3 does. And then continue. Can't break down 3, but it can break down 15 to 3 and 5. And now we can write this as a product of all the primes. So it's 2 times 3 times 3 times 5. Or rewriting the 3 and 3 as 2 times 3 squared times 5. And we get our final answer. Alright, the second method that some of you may have seen is the birthday cake method. And how you start that is, you put your number at the bottom and you use the division bar. And the same thing, we want to find what's the smallest number that's prime that goes into 90. Well, we know it's 2. So when we divide 90 by 2, you get 45. And you add another layer to the cake and repeat the process. There's my next layer. And we keep going. Well, what's the smallest prime number going into 45? It's 3. So we're going to add another layer of the cake, and we know we get 15. This 3 times 15 is 45. We do it again. Well, what number goes into 15 that's prime? 3. And we get 5. And finally, what's the only prime number that goes into 5? Well, 5. And the last thing we have, we know we're done with our birthday cake problem, and we have our candle on the top. We got the 1 on the top, and we've got ourselves cake, 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 and our candle. Alright? Our prime numbers are outside. 2 times 3 times 3 times 5, and you get 2, 3 squared times 5. Alright. Okay. Now that you have some time to try these, let's see how you did. So the first one, prime factorization 84. I show both methods here, but if you're going to factor tree, I use 2 and 42 to start. and then 2 and 21, finally 3 and 7, and you get 2 squared times 3 times 7. The birthday cake method, very similar. Start your base layer of your cake, and you go 2 goes in 84, 42 times, 2 goes into 42, 21 times, 3 goes into 21, 7 times, 7 goes into 7, 1, candles on the top. Same answer. Your choice on which method you'd rather do. Some people would rather do the division. Some people would rather do the factor tree. For number 2, I just did the factor tree, but pull the -1 out first. Once the -1's out front, then you can just do your factor tree or your cake method, and you would come up with -1 times 2 squared times 3 times 11. Okay, for the next problems, it says prime factorization of a monomial. And it says factor each monomial completely. For these problems, all we're going to do is do the prime factorization of the number in the front, and then instead of having exponents, we're going to write out the variables. So for the first one, we got to do the prime factorization of 12, 2 and 6, 2 and 3, and we're done. So we know it's 2 times 2 times 3. Then, and we can't have any exponents if it's monomial factored completely. And now, instead of having a squared, we know that's a times a. Instead of having b cubed, we know it's b times b times b. And we've successfully factored our first monomial completely. Alright, so for letter B, we're going to do the same process. We're going to do the prime factorization of -66, and then we're going to rewrite our variables so that there is no exponents. So, -66 can't have the negative. Pull the -1 out, and 66. And then we have to do the prime factorization of 66. So we got 2 and 33, 3 and 11. Can't go any further. So our numbers, -1 times 2 times 3 times 11. And now with our variables, we can't have exponents. We have a times b. Alright, after you had a few seconds to try these problems, let's take a look. So we start off with the first example, example 3, and we need to do the prime factorization of 32. We come up that it's actually 2 times 2 times 2 times 2 times 2, and then only final thing we have to do is rewrite it so we don't have any exponents for our variables. So you can see we got 5 2's all being multiplied, 2 x's, 3 y's, and a z. On the next problem, with -48, remember to take the -1 out first, and once that -1's out, you can do the prime factorization, and you can see the last part at the bottom here, our answer is that there is no exponents, rewriting those variables out as times each other. Alright, so the last thing on this notes for tonight is the greatest common factor. The greatest common factor is the greatest number that is a factor of both original numbers. To find the GCF, typically, most people like to do finding the GCF, they apply prime factorization that we dealt with earlier. So, for letter A, we start with doing the prime factorization of 15, 3 and 5. We can do the prime factorization of 16, 2 8, 2 4, 2 2. If, as we see in letter A, we have no factors for our prime numbers that are in common, then there's only one factor that they share. Big old I am number 1. For letter B, we see variables and we see numbers, and some of you are going, oh boy, you know, oh girl, we're not sure what to do. Well, no need to fear prime factorizations here. On letter B, you start with the prime factorization of 36. Well, let's break it down a little bit. 2 and 18, 2 and 9, 3 and 3. Let's take care of 54. 2 and 27, 3 and 9, 3 and 3. And now, when we want to find the greatest common factor, we often take pairs because we know that the common factor, if we can make a pair of prime numbers, that it's common to both. So I can make up one pair of 2's. Once a 2 is used, or once a number is used, you can't use it again. So there is no 2 for this to make a pair with. But I can make a pair of 3's. I have another 3. I can make a pair of 3's. But the 2 and the 3 that are left here, there's no other number that we can pair up that we haven't already used. So for the number, for the coefficient out front, we just need to multiply these together. So we got 3 times 3 is 9, times 2 is 18. So the GCF of the two numbers would just be 18. Now, we look at the variables. The rules with the variables is that you take the lowest power of common variables. So you look at the letters and you say, well, what letters do they have in common? They've got X and they've got Y. You want to take the lowest exponents on those variables. So we've got X squared and X to the first. The lower of the two would be X to the first. You have Y to the first and you have Y squared. You take the smaller of the two, Y. They don't have Z in common. Just like we saw here, when there wasn't a variable to pair up with, just like when there was no number that we could pair up with that hasn't been used, it does not get included in the greatest common factor. And you successfully done one with variables. For example 3, starting off with 48 and 60. I broke down 48 and I got my prime factorization was 2 times 2 times 2 times 2 times 3. And then I broke down 60. I moved it over so you could have a little more space to see it. And I got 2 times 2 times 3. I started pairing up. Well, I got a pair of 2's. I got another pair of 2's. I got 1, 3. The other 2's, I can't make a pair on the same side. This is a common mistake that some people will do. They'll say, oh, there's 2 2's, so I'm going to match them up. No, no. Okay, can't do that. They got to be compared between the two numbers or even 3 numbers, which you'll see in class tomorrow. Can't wait. Okay, but we have 2 times 2 times 3 left. Well, 2 times 2, 4 times 3, 12 for our GCF. The last one with our monomials is start off with the numbers. Well, I took down 27. It was a bear, but I took it down to 3 times 3 times 3. Took down 15 to 3 and 5. Made my pair of 3's. Can't do anything else. I know, common thing. Hey, there's 2 3's. Let's match them up. Can't do it. Then took your variables. Take a look. You take the lowest powers on the variables. So I got x2, x1. Taking the x1. Got y2, y3. Taking the y2. Got z2 and I have no z at all. Got to take no z at all because there's not in common. It's got to be the greatest common factor. That concludes today's class, and I'll see you in class tomorrow.